Hello, and I'm here to talk particle physics again. Yesterday, or last video rather, we looked at baryons and mesons. Today we are going to look at leptons. Okay, and what I'll do is I'll talk about the practical applications of this instead of this essentially just looking like showing off with letters. So in the previous video we discussed baryons, and we discussed baryons being made of 3 quarks, and the quark combinations depend on charge and the type of baryon you're making. So for example, we talked about how a proton is made from 2 up quarks and a down quark. Okay, mesons are a quark and an anti-quark combination. Okay, and you've got different mesons such as pions and kaons, and you can figure those out using the data sheet. Today, what I'm going to talk to you about are leptons. Okay, now leptons are a fundamental particle, which means they are only made from themselves. Okay, examples of leptons are the electron, which we give the symbol E. There's the heavy electron, we call the muon, which we give the symbol mu. And there is the neutrino, which we use the Greek symbol nu, which kind of looks a bit like a V. I'll get rid of the commas to avoid confusion. Okay, so these do not experience a strong nuclear force. Okay? In fact, they only interact through the weak interaction, which is something that we can go through when we look at Feynman diagrams. Okay? These have also, I'll use a black pen to change it up, these all have a lepton number of 1. Okay, because they're a lepton, so its lepton number is equal to 1. Okay, you've also got positrons, anti-muons, and anti-neutrinos as antimatter versions of the leptons. These are all anti-leptons, and these have got a lepton number of -1. Right, so let's have a look at the implications of this. So let's talk about beta negative decay. Okay, so for beta negative decay, we know that a neutron changes into a proton, and that releases an electron, and it releases an anti-neutrino as well. And we show that it's anti by putting the bar above it. So this, if we review the lepton number for all these, this has got a lepton number of 0, because neutrons are not leptons, they're baryons. This has got a lepton number of 0. Electron has an lepton number of 1, and the anti-neutrino has got -1. We've got 0 on the left, and we've got 0 on the right, because +1 plus -1 is equal to 0. Okay, so that's why it's important that the anti-neutrino exists, which we'll not have discussed at GCSE. Another law of conservation that we must consider here is the baryon number. A neutron is a baryon because it's made of an up quark and 2 down quarks. A proton is a baryon number of 1, and these are leptons, so they have no baryon number. 1 and 1 on both sides, so we're happy. Last of all is charge. A neutron has no charge. This is +1 for a proton, -1 for an electron, and this has no charge. So we've got 0 on the left and 0 on the right. So that's why leptons are important in conservation, and that's why we're not just showing off with physics, although we kind of are. All the best.